And I will I will hand over to Margaret to introduce the speaker.
Okay.
Yeah. Thank you. So welcome back to the second talk of today's ZORP. And so we are very happy to have Arda Demirhan from the University of Illinois at Chicago, who will talk about distribution of rational points on toric varieties, a multi-height approach. Please, Arda.
First, I'd like to thank the organizers for inviting me for this wonderful seminar series about rational points. And yeah, good evening, everyone. And as I said today, I'll be talking about distribution of rational points on toric varieties. And this is part of my PhD thesis under Professor Ramin Taglabigash. And I don't know how this goes, but I'll be checking the chat window at the end of the talk. But I guess there's also, the Gather Town meeting, so I will also be taking the questions there. So let's get started. To understand the distribution of rational points, we need to know how to count them. Say X is an algebraic variety in the projective space Pn over a number field, an algebraic extension of rationals. Then to count rational points, the main idea is to use height functions. I mean, heights are useful. Height functions are useful because one can translate geometric facts given by divisor relations to arithmetic facts given by height relations. It is like a dictionary. So to a divisor, height machine associates a height so that relations between the divisors converted into relations among heights, arithmetic facts among heights. More precisely, I mean, what we do is, for very ample divisors, there's an embedding from the variety to Pn. And that means that the height function for very ample divisors is just the usual restriction of the projective space to the variety. But as we know that arbitrary divisors can be written as a difference of two very ample divisors, and height machine ensures that the choice of this embedding that we are talking about affects the height only by a constant. And but we don't need to worry about it because by metrization, by putting a metrization on them, we also fix that difference by a constant. So this construction works in the more general setup over any field with a proper set of absolute values satisfying the product formula, which will be crucial throughout the talk also. For example, there is a theory of heights over function fields. In fact, Arakelov geometry introduces special metrics. In the Arakelov geometry, we define extended divisors, which entirely reconstruct the height theory in a geometric fashion. And that can be also translated back into the number theory setting using complex analytic constructions such as Hermitian metrics, or using some special schemes over Dedekind domains. So we get back to the number field setup. So we have the slogan, geometry determines arithmetic, because knowing something about the geometry of the variety tells something about the distribution of rational points according to height. Let's get into the definition of the counting function. We consider a Zariski open set with some rational points. I mean, we want to ensure that this we have some rational points. We don't want to work with an empty set. Then we define the counting function as an UKB as the cardinality of k rational points of U whose height h is bounded by B. The thing is, the asymptotic behavior of this function can be analyzed in many different ways. Like we can take the algorithmic point of view, and it turns out that it is a very difficult, in fact, undecidable problem. But luckily, I mean, yeah, we are interested more in algebraic geometry, and what we have is asymptotic behavior of the counting function depend on the geometry of the algebraic variety. For example, genus is a geometric invariant for curves. When genus is 0, the growth is given by a constant times b squared. When it is 1, the order of growth is a constant times log b to the power r over 2. And when g is bigger than 1, it is just a constant. And I can say that another important geometric invariant is the canonical class. There are several reasons that the canonical class is so useful as a geometric invariant. Like, to name a few, it is very easy to compute, and there's the injunction formula. But maybe, like, yeah, we are doing zoom on rational points. So maybe for us, probably the most important thing is by using it, we can state one of the most famous like conjectures in arithmetic geometry, which is Manin's conjecture. So let's say we have a Fano variety. It means that the anti-canonical class is ample, almost like very ample. I mean, yeah. So that also, I mean, in the definition of Fano variety, we ask the variety to be complete. Then we have the following. I mean, the conjecture. Let's say we have a nice variety, meaning that smooth and projective. In some setups, we like to work with geometrically integral varieties. Then there exists a finite field extension f of k with f rational points being dense in x, and moreover, yeah, we have this following formula: number of f rational points of u bounded by h, bounded by b, is given by a constant times b times log b to the power t minus 1 times an 1 plus O1, an error term. Here, T is the rank of the Picard group, and of course, we are thinking as b goes to infinity. Like, I'll be talking about accumulating varieties today a bit. So, like, in fact, like to state Manin's conjecture, we might have to throw away the accumulating subvarieties to get the corresponding asymptotic formula, like in a right way in Manin's conjecture. I said that Manin's conjecture is a very famous one, but the funny thing is it is also famously wrong. And for example, Batyryev and Schinkel provided the following example. So say xn plus 2 is a hypersurface in the product Pn times P3, and given by this equation. And here, yeah, n is bigger than 2, and li's are linearly independent, and x underline means x not up to xn. And say xn plus 2 is as, yeah, I mean, it turns out that xn plus 2 is a smooth Fano variety. So yeah, it satisfies the first assumption. And again, we see that there exists an open set, let's call it as un plus 2, a Zariski open set in xn plus 2 with isomorphic to an plus 2. So in a way, we embed a copy of the affine space into xn plus 2. So the Picard group of xn plus 2 is just a direct sum of 2 copies of Z. And most importantly, probably, there exists a number field K0, which depends on U itself. And it contains the imaginary quadratic field Q squared of -3. such that for every field extension k of k0, we have this formula like the growth of u, like k0 rational points of u bounded by b is bigger than or equal to the like the number of that is bigger than or equal to a constant times b log b cubed. So that means therefore a Manis conjecture fails. And one nice thing is it is not a single example, it is in fact a family of examples. Okay. Yeah, but the thing is, yeah, I mean, this was a counterexample. Like, if we all had failure, then like probably like many of us work with Manis conjecture, so it would be super bad for us. Life is not that bad. Luckily, there are some good examples that we are all working on. Like, yeah, Manis conjecture is true for some classes of varieties, including like Toric varieties, the topic of today's talk, some equivariant compactifications, flag varieties, smooth complete intersections of small degree, and like also horospherical varieties. Like, for example, for smooth complete intersections, as far as I know, like people working on those by using circle method and an analytic tool. As I said, like on Fana varieties, we shall have to remove the accumulating subvarieties with respect to the anti-canonical class if you want to ensure the linear growth conjecture. I mean, what I mean by linear growth conjecture is the growth function that I like gave here, I mean, defined in the previous slides, grows like a linear function asymptotically. So let's start. Yeah, I mean, I already mentioned accumulating subvarieties. So let's see a definition of it. First, we need to define the height zeta function in the abstract setting. Say U is a countable or a finite set. I mean, suppose we have a function from U to R plus, and I mean, we of course, like this letter H suggests that this will be a height function, such that its growth is finite for all the B's, for all the bounds that we have. Then we define the zeta function as like it depends on U, L, and S. I mean, S is the parameter, as the sum of the S powers, reciprocal of the S power of the HL function, over where the sum is over all the points in the U. I mean, here L is a line bundle, and like as we all know, like line bundles can be characterized as with divisors. So hence by the height machine we have the function, the one-to-one correspondence, and like this is not the most formal setting yet, but we will be getting there. Like in algebrogeometric situations, by L we mean not just L, but L together with a data metrization. So like, yeah, we can define the abscissa of convergence, which is a very important tool, as beta. It depends on U and L, beta UL, as the infimum of all real numbers, so that this series ZULS converges for when the real part of S bigger than sigma. And like one thing is, this number exists. I mean, it can be infinity, of course. Like, yeah, now let's see the connection between abscissa of convergence and growth for a height function. Like if U is finite, it is trivial. I mean, the abscissa of convergence would be then negative infinity. Otherwise, it is given by maximum subsequential limit of the ratio log and LUB and log B. And one nice thing is, if I recall right, I think, yeah, by product formula or yeah, by the very like proper properties of height. The beta doesn't depend on the choice of the height. And now we can define what an accumulating subvariety is. A subset X of U is accumulating when the abscissa of convergence for U is equal to X. Beta UL is equal to beta XL. But the more important thing is maybe we ask for this to be bigger than in the complement. So this is bigger than beta of U, the complement of X in U of L. So like that roughly means that we push the abscissa of convergence down after deleting it. But I'd like to say something there, like there are different formulations for accumulating subvarieties. I mean, different looking maybe, like in the literature. Also, like people like classify, like, there are kinds of accumulating subvarieties, like things like strongly accumulating, weakly accumulating. I mean, I won't be getting into all those details, but in any case, accumulating subvarieties yields a better grasp of the distribution of rational points. That is the most important thing about it. So before getting started with toric varieties, let's see an example, an accumulating variety example. Here, I'd like to talk about the example where we blow up Pn along Pm. So, yeah, I actually have a funny story about, like, anytime I talk about blowups, like once I was coming from the math conference, and like in the plane I was talking about blowing up, and talking about this in a non-math setup is a bit funny. Anyway, so here, let's say m is at most n-2, and let's say L0 is a linear subspace of Pn defined by the equations xn plus 1 up to xn, and so that means L0 is isomorphic to Pm. Let V be the blow up of Pn along Pm, which is L0. There's some. Is there any problem or? Yeah,
no, you said something about blowing up. I said at least you're not Iranian. Well, I am.
Yeah.
Anyway,
Okay. Hi, yeah.
Dumb joke. Hi.
Yeah. Okay. So yeah, L0 is isomorphic to Pm, and I mean, we have blow up of Pn along L0, and like explicitly, this guy is just the zero locus of the functions xy, yj minus xj, yi, where xi's are coordinates from Pn, coordinates in Pn, and yj's are coordinates in Pn minus m minus 1. I mean, the coordinates after m up to n. So let's say we have projections P1 and P2 from V to Pn and V to Pn minus m minus 1. So let's say L is the pullback of a hyperplane by pi 1. So yeah, which is a hyperplane section, and say E is the product L0 times Pn minus m minus 1, which is the exceptional divisor of the blow up. And it turns out that they satisfy the following. Like pi 1 is an isomorphism from the complement of the exceptional divisor in the blow up to the complement of L0 in Pn. The Picard group is a free group of rank 2 generated by L and E. The canonical class is given by the combination negative n plus 1 L plus n minus m minus 1 E, and by a by Nakaya-Moshazan criterion, it's something you can like. I think it appears in chapter 5 of Harshorn, like an effect in algebraic geometry. We can characterize ample divisors by AL minus BE, where A and B are positive and A is bigger than 1. So, with respect to the height, associated to the divisor AL minus BE, I mean by the height machine, number of rational points of E and U bounded by B are given by this like kind of messy looking expression, piecewise defined thing. I mean, in short, the relation between A, B, M, and N change things, change the growth. And in fact, this is a well-known result, an exercise in Sar's book, I think in lectures in modern array theorem, or also in Henry Silverman's one of the exercises in the last chapter. It turns out that E is an accumulating subvariety for the anti-canonical divisor, and that's the reason why we actually went through this, and one of the reasons. And like, if you want to work with a like smaller values, like setting n to 2, m to 0, we see that the exceptional curve of the blow up of the projective plane at a point is accumulating for the anti-canonical divisor, which is 3, 1, generated by 3 and 1. So yeah, one of here the blow up of Pn along Pm is a toric variety, and that's the second reason why I picked this as an example. Motivated by this example, we see that the multi-height approach removes the effect of accumulating subvarieties for toric varieties. So before getting started with toric varieties, I'd like to point out there are several methods that have been employed to study the distribution of rational points on toric varieties. For example, harmonic analysis was used by Batyryev and Schinkel, and also by Strahan and Schinkel. And I believe, yeah, I mean, these are the sources that I use the most. So that doesn't mean that this list is exclusive. Yes. And on the other hand, Salberger and Dolaberitesh employed universal torsors. I mean, for the method of universal torsors, the idea is to relate points on a projective variety to integral points of the universal torus of the variety. And naive example would be the one-to-one correspondence between Q rational points of Pn and primitive n+1 tuples of integers. But of course, I mean, this is not as complex as this. It's just too simplified example. There are also the circle method, dynamics, ergodic theory, along with elementary tools as a toolbox to treat Manin's conjecture in some particular cases. But yeah, our method is based on harmonic analysis. Before getting into the idea, I'd like to say that, yeah, we'll be working on toric varieties. So a toric variety has a large automorphism group. And hence, the harmonic analysis, gets into the picture right there. I mean, because of that. So let me give a brief outline of an argument using harmonic analysis for tori. We define a height pairing on the product of the group of isomorphism classes of T-linearized line bundles and the adelic points, such that it is invariant under a standard compact subgroup of adelic points. We define the height function, and thanks to the projectivity of the toric varieties, it turns out that the height function will converge in some nice region, like in some open cone in the group of T-linearized line bundles. As you see, the T-linearized line bundles play a very crucial role throughout the discussion. Then, of course, yeah, I mean, yeah, this is an analytical business. We apply a Poisson formula and to get a representation with an integral being over characters, and these characters are trivial on the k-rational points. This is crucial. Then we compute Fourier transforms at almost all non-Archimedean places and get estimates in the rest of the Archimedean places. And yeah, the second to last, we get a meromorphic continuation and identify poles. And finally, we hit it. I mean, we kill it by using a Tauberian theorem. And so let's start talking about toric varieties and yeah, toric varieties, which is the topic of today. So First, we need to define what a torus is. A torus is a linear algebraic group T over a field K, such that its base extension to the splitting field, let's call it as L, is isomorphic to a finite product of multiplicative groups. Like some tori are nice, and we don't need to do this base extension. Like, in fact, in some textbooks, it is represented in a way that there are no bad examples. I mean, at the first time, I remember I thought that all the tori are split. But yeah, of course, there are non-split tori. And in this case, yeah, these guys are the ones that are automatically isomorphic to a product of multiplicative group over the field that they are defined. We have characters T hat as the hom T to K bar star. Like there's a nice categorical correspondence between algebraic tori defined over a number field K and discrete continuous Galois K bar over K modules over a finite rank over Z, given by like we send a torus to its character group T hat and conversely send such a module to a spectrum of Km. One nice thing about this is this equivalence is functorial under field extensions of K, and which yields a contravariant equivalence between E split tori over K and Galois E over K modules. Yeah, I'll be getting to anisotropic tori now. Like, if G is the Galois group of the splitting of a d-dimensional torus T, then the G module structure on the free abelian group of T hat is given by an integral representation rho from G to automorphism of T hat. I mean, automorphism of T hat is isomorphic to general linear group of order D over integers. Now, I mean, then T hat K is nothing but a sublattice of T hat consisting of all G invariant elements. And finally, a torus is anisotropic if the rank of T hat K is 0. In other words, it doesn't contain any K split tori except the trivial one. So, like, for example, orthogonal groups of quadratic forms which are not vanishing over Q or any field, in fact, are anisotropic. And it turns out that all K points of a toric variety, yeah, like, we'll be getting into proofs, all the details, but yeah, one of the most important thing is that it, yeah, like all the K points of a toric variety are in fact contained in the torus itself when T is an anisotropic torus. So this is in fact one of the crucial things which appears in the paper of Batyryev and Shinker about anisotropic tori. Okay, so to define what a toric variety is, we need some combinatorial data trends. I will be giving the data for split tori, yeah, non-split tori. Yeah, there are also non-split tori, but just for simplicity, I will be giving the data for split. Suppose we have a free abelian group of rank, of finite rank M, dual abelian group N, and real space, which is the tensorial extension of N. Then a fan is nothing but a special finite collection of cones such that 0 is in the fan. We ask every face of every cone in a fan is a cone itself in the fan, and we also ask intersections of two cones in the fan to be a face of both, and then by the second property, it is also in the fan. Like, some particular fans are easy to work with. There are complete fans such that the union over all cones and complete fans gives the whole real space NR. So there are also regular fans. These are the fans such that generators of cone form a part of a basis of N. Now, I mean, we can construct a toric variety from a fan just by gluing together all affine toric varieties of the cones given by the spectra of some special polynomial ring, where sigma check here is the dual. So let's see an example. Say sigma is a fan, d-dimensional fan with one-dimensional cones generated by like the first d elements are the canonical basis elements. The last one is different. It is the sum of the opposite of the sum of the rest. And say m-dimensional cones generated by m subsets of them. And once you glue the affine toric varieties all together, what you get is nothing but PB, the projective space PB. Let's make some crucial observations. The one-dimensional generators EIs of sigma corresponds to boundary divisors invariant under the action of T. And that also corresponds to reducible components of the complement of T inside X sigma. The thing is, as I said also already, the notion T invariant boundary divisor is a very restrictive, strong notion. I mean, we are not just talking about divisors. I mean, like if we do, then I mean, there are tons of divisors, like all the hyperplanes in PN are divisors. So this is something strong. And one last thing is regular fans are nice because the variety that we build from that is a smooth variety. So before getting into heights in the setting with metrization, let me state an important correspondence between sigma piecewise linear integral functions on NR and group of T linearized line bundles on the toric variety. This is given by assigning, I mean, a piecewise phi linear function phi to the subsheaf LP of constant sheaf of rational functions on the toric variety, generated by m sigma phi's, which is the restriction of phi to the cone sigma. This thing is an exact sequence, and by this correspondence, we can replace PL sigma by T linearized line bundles. Every such divisor is equivalent to a linear combination of boundary divisors. One thing I'd like to say there is phi is determined by its values on EIs, of course, and we denote their values like phi I EJs as SJs. And relations among them come from characters of T because we consider m sigma phi as characters of T. Now we can talk about building height functions. To obtain a global height, like as a product of all local heights over all variations, first we need to have a working knowledge on local heights, of course, but it depends on the type of the valuation. For the non-Archimedean case, it is h sigma v x v phi equals to exponential of phi x bar v log qv. Here, x bar v is a representative of the kv rational point of T in some special quotient space. One striking thing is the product formula ensures that the choice of the representative, like, I mean, the global height function is well defined in the sense that the choice of the representative doesn't change it. And QV, like here, QV is the cardinality of the residue field of the completion of K with respect to V. And like for the Archimedean case, yeah, we don't have it. It's just the exponential. So let's see an example height computation. So say we have P1 and peak TP1 generated by the classes of 0 and infinity. And say S is equal to 2, 3. And that means, of course, like S1 is 2, so phi of E1 is 2, phi of E2 is 3. And just by using that, we see that the local height can be computed like this piecewise function. And then we can just take the product over all valuations to get the global height. By using global heights, we define the height zeta function just as we define Riemann zeta functions. Like, in fact, I already defined it for the less abstract setting. Here, z sigma phi is equal to the reciprocal of h sigma x phi's, where the sum is over all k rational points of T. And yeah, I mean, yeah, in this definition, I'm summing over the points, k points in T, not the whole toric variety. And one thing that we all expect is, and yeah, I mean, naturally, this definition is inspired by Tauberian theorems. And like height zeta function enjoys some nice analytic properties, like Poisson formula is one such. For the anisotropic case, I gave the expression there. Like we write Height zeta function as the sum of Fourier transforms, h hats over characters of up to a constant. Like here, as I said, h hat is a typical Fourier transform with respect to the adelic measure. Like the adelic measure omega it doesn't depend on the choice of the capital omega, which is a T invariant differential form, by the way. S is a finite collection of all variations containing all Archimedean variations and ramified non-Archimedean variations in a finite Galois field, extension field. And what should I say? Yeah, BST is the volume of the quotient with respect to that measure. And the most important thing is, for the general isotropic case, we are not just summing over the characters, but there's an integral, separate integral expression. Now, I'd like to point out, show an important proposition of Varieties and Schinkel in their paper on anisotropic tori, like compactifications of anisotropic tori. Like height zeta function is holomorphic when real part of all coordinates is bigger than 1. And this guy can be meromorphic. We continue to the left of this line with poles along the line has order at most 1. Since we want to use Tauberian theorems, we need to know analytic properties of height zeta functions. In the work of Varieties and Schinkel, they restrict phi to a single line to verify Manin's conjecture for toric varieties. This is a key step in their argument. And they only use a single metrized height function. In our situation, like in our work, the key difference is we don't consider this restriction at all. Instead, we consider the multi-height approach suggested by Emmanuel Peyre. Like, in fact, he combines both freeness and all the heights approach in his papers, Liberté Accumulation and Beyond Heights, Slopes and Distribution of Rational Points. These things are useful because we may eliminate the effect of accumulating subvarieties in some cases. So we'll be applying Peyre's multi-height approach for toric varieties. One side note here is that I had a personal conversation with Peyre in 2019 in the Phono Varieties conference in Paris. He suggested using all the heights approach rather than freeness approach. And moreover, I also had a conversation. William Savin from Columbia has a recent paper in 2020, like where he shows that freeness alone is insufficient for example, the Hilbert scheme. And roughly speaking, replacing accumulating subvariety by the collection of points where the freedom counting function, the freeness is small, is not an efficient method. We need to combine with all the heights approach. So anyway, we'll be just working on all the heights approach today. And we'd like to examine the behavior of the growth function in the multi-height setup. More precisely, by considering all the metrized heights determined by T invariant DIs yielding the ample divisor, the sum of SI DI, what we do is we count the number of k-rational points in some rectangular boxes as b goes to infinity. The one very important remark here is we are not throwing away any accumulating subvariety, so not just counting the points in the torus, but in fact in the toric variety, the whole variety. Now our main result tells us about asymptotic of this growth function. Like for some positive real constants, p beta and theta, the growth is given by some exponent b to the power the sum of beta is just a vector times the constant p beta plus an error term or b to the negative theta as b goes to infinity. We'll first see that it is enough to show that for the open piece, the torus, rather than the whole variety, the key point is that the fan of the toric variety completely and explicitly determines the fan of any T invariant divisor as a toric variety. Hence, we can do an inductive argument on the dimension of the toric variety. So getting into details, we consider an equation in this form: d1 is equal to t1 union d1 minus t1. Here, the complement of t1 in d1 is just union of all boundary pieces. The crucial observation is that we can replace the data x delta t1 up d1 and up to dr with d1 comma t1 up to dr, removing the d1. More precisely, if we can show that the f rational points of t whose multi-heights are bounded by some exponents of beta, b then is equal to a constant times some exponent of b plus an error term, then we can show the similar thing for the k-rational points of the toric variety. I mean, with heights, this time heights again bounded by the same values, and it equals to the same expression. And since the complement of t is equal to the union of boundary pieces, so it is enough to show that the points in d1, f rational points of d1, whose heights are bounded by those exponents, is equal to the error term, that error term b to the power sum of ai's minus an epsilon, and f points in t1 whose second height up to r height is less than b to the ar. It's equal to the same. The cardinality of the same set, this set is equal to the some error, like some expression. So by this inductive argument, the problem of counting boils down to counting rational points in a general, not necessarily anisotropic tori setup. Hence, we don't need to work in the full toric variety. We can just do our work in the torus, and that's why we can consider the height zeta functions on the torus only. Let's go over the sketch of the proof for the anisotropic case. We consider the arithmetic function. What this guy does is it does count the number of times that rational points get some particular coordinates values on their multi-heights. Based on that, we define an analog of multi-height zeta function, which is a multiple Dirichlet series, by the way. This is a countable sum, and if, as you can see, like if we set m to 1, this becomes a single variable height zeta function as appeared as we defined. So in a way, fs generalizes the height zeta function, and yeah, f satisfies some nice properties. Fs is absolutely convergent when the real part is bigger than 1, and here 1 is of course the tuple. Like by the definition of C, we know that Fs involves the sum of the terms, the reciprocal of the product of HIS SIs up to a multiplication by a constant. But by Wey's height machine, I mean, we know that heights are multiplicative, so we have that the reciprocal of the product of heights is equal to the reciprocal of this height with respect to this the linear combination SI DI. And like here, DIs are T invariant divisors providing a very ample divisor, and SIs are in the complexified Picard group. And taking the sum, we obtain what we want. I mean, Fs is equal to Z sigma. Now, by the theorem that I showed, by the theorem of Bateyev and Schinkel, we are done with that part. So by shifting the variable over the counter and clearing the poles by multiplying with a coordinate function, we get a nice function h, which is nice. Like, I mean, nice means holomorphic in some special domain. And here, like pi i's are coordinate functions, and the domain is it's just I mean, we ask the real parts to be bigger than some negative constant for all I, and yeah, like we can use the Fs is equal to Z sigma, and again by the same theorem the claim follows. The most interesting part of the argument is like the argument of the anisotropic tori business is the P3. Well, I'm calling it as the property 3 for all epsilon and epsilon prime. I mean, HS the HS is equal to the growth of HS is equal to a fancy term. I mean, like it looks horrible, but it is. Yeah, I mean, yeah, this thing is also uniformly valid in some special region when real part of S be less than 1. I mean, although I said this looks fancy, all it says is H has moderate growth in vertical strips. Like this is what we want to get from this expression. This is the key thing. Like Poisson formula, like here, the Poisson formula applied to the height zeta function gives a discrete sum over a lattice of characters. I mean, because we are in the anisotropic case. And again, by referring to the same paper of Vatiliev and Schinkel, we get this domination estimate from the standard bounds for L functions and integration by parts. So now I'd like to bring the point to the Tauberian theorem of Demirhan, because we are right there. I mean, this is the exact location that we need to talk about. Say we have an arithmetic function on Nm, and say we have its Dirichlet series with these properties. Then, yeah, the conditions are like we want this guy to satisfy three properties: P1, P2, and P3, as I said in a parallel way for the argument. So we ask Fs to be absolutely convergent for S when real part of S be bigger than alpha. Alpha is a tuple, positive tuple. We ask an existence of a family of non-trivial linear forms and another such linear family, not necessarily non-trivial, such that, I mean, same type of thing, HS, like shifting the contour and multiplying with Li's, like clearing the poles. We get a nice function in some special domain. And finally, we ask existence of some special domain. And in that domain, we ask for moderate growth in vertical strips. Then, I mean, if F satisfies all these nice properties, then it turns out that the sum over all di's less than x to the beta i's, the sum of all f di's over di less than x to the beta I is equal to some exponent of x given by the inner product of alpha and beta times a polynomial QB log x and plus an error term x to the negative theta. Like here, as I said, Q beta is a polynomial in Rx and theta is a constant. I'd like to point out a few things. Like here we had alpha. In our argument, remember, like it was 1. So the one important thing there is, I didn't put that detail here, but QB is a polynomial of degree, like the degree of the polynomial depends on n, the number of trivial terms of alpha, let's call it as R, and also the rank of Li's. The key thing is n is n, I mean, but the point is number of trivial terms of alpha, I mean, in our case, alpha is 1, 1, 1, so it is 0. And since Li's are coordinate functions, they are all linearly independent, so that is equal to n. So this is just n minus n plus 0. So that's why the degree of QB in our Q beta in our situation is 0. Hence, we have the constant P beta. And yeah, one thing is, yeah, here we are not like the finite family of HR is just an empty set. Like we only have Li's in our setting. And what else? Yeah. One thing I'd like to say is, as you can see here, the sum in Demirhan's theorem is over. I mean, he has a Dirichlet series where he sums over all integer tuples, positive integer tuples. Whereas, remember, where is that? Yeah, we were doing the sum over countable set C, but like his proof for his theorem works for our case for C2, because what he does is like he uses. Let me get back to he uses some sort of Gaussian elimination with pivoting and some residue calculus, so it just works for any countable set. Now, in the last part of my talk, I'd like to get into details, the most general case. So we established the proof for the anisotropic case. I can talk about the general case. So the ambient space is RP. We take its complexification. We take a subspace. And we want to work with some nice functions called sufficient. These guys are absolutely integrable. And the second property is, I think, the most important one. The thing is, like the people who are using the covariant theorem of Demirhan, for example, Munch and Sparlinski use the same for their problem. I mean, what they are interested in the setup that real part is bounded. So in a way, real part is not the issue. The issue is the wild imaginary part. And in the one-dimensional case, let's say V is a one-dimensional thing, and like if we have something of the form I times X, where X is a real, the second notion plays a key role, because thanks to that decaying property of C, I mean, it plays a key role in our argument to show that our argument works in the general setup. That's I'd like to say. So we can also talk about the distinguished functions. Technical setup in the for the distinguished functions. Say we have linearly independent linear forms on E, and we have a convex and open neighborhood of 0 such that Li's are bigger than -1. Then we want to work with in a tube domain TB, B plus IE, and say f is a meromorphic function in TB. Then we call a function as distinguished. It is pretty much like the in a fashion closer to the Liberté setup. The difference is G is given by, there is the denominator LJS plus 1. I mean, this is different. Why? I mean, this is the only difference with HS, capital of HS. But I mean, the denominator doesn't create any problem, because I mean, that's the reason why we ask in the setup of P, we ask for LJX to be bigger than -1. So if a function is distinguished, then it satisfies that this G function is holomorphic in TB. And we also ask G to have a moderate growth. Kappa is a constant for all compact sets. So GS plus IV is less than kappa times CV. So if we want to work in a connected component of B, and we want to work away from the zeros. I mean, because I mean those zeros, we don't want them to be appearing in the denominator. And on TC we define the f tilde function as the d-dimensional integral of f, and then we have this important theorem of Strahan-Schinkel. It turns out that f tilde is holomorphic, and for some open and convex neighborhood containing 0 and containing C and some linear forms, we have that this function has a holomorphic continuation to TB. So to finalize, I mean, in this state, I mean, let me wrap up all the details for the proof. In the statement of general Poisson's summation formula, there's a sum over all characters of an anisotropic torus, followed by a d-dimensional real integral. Like to apply de Liberté's multidimensional Tauberian theorem, we need to verify the conditions of theorem by doing induction on the dimension of D. And then it turns out that the anisotropic case is just the base case. More precisely, we consider a function given by some d-dimensional. As I said, this function will be the integral of a distinguished function. And it is not just a distinguished function. Here the f without the tilde is roughly a sum of h hats. And nice thing is f tilde matches with the height zeta function up to like some constant in the general case. And then we are done by using the machinery of Strahan-Schinkel and doing induction on D. Yeah. And final remarks. As we mentioned before, this computation is for the open part, and we need to do the induction on the piece of Toric variety. And once we show it for the open piece, then we are done and everything just follows. And what I can say is this is still a broad outline of the argument. There are still lots of technical details that needs to be taken care of. I'd like to, thank you for coming and listening to me, and that's the end of my talk. So, sorry. So,
thank you very much, Arda. Are there any questions?
So I have a question actually. If I understood correctly, you mentioned that you'd considered trying the freeness approach.
Can I interrupt for a second? I'm sorry for that. I got an emergent. Like, sorry.
Yeah, no problem.
Sorry. Let me. Hello. You can hear? Yeah. You can leave it there. Like we will the proof of the level test in this